Hello, everyone. Could you hear me?
Yeah, I can hear you.
Okay, great. Thank you. Um, now, um, today we will talk about um, the buffer overflow attack. Last time we talked about um, in assembly how we deal with some data structures like array, struct, union. Um, we talk about um, we talked about in the assembly, the key is to geolocate certain items in the structure. That's where we talk about some mathematical equations we can use um, in order to find what is the address of a certain item. The later part of last lecture, we talk about um, how we um, so how we so how we deal with the data alignment um, situation. Um, it turned out we don't use our memory randomly. We hope to we hope to have our memory to use. Let's say we have an object of size k bytes. We want to use the address which is a multiple of k to hold that object. That is a data alignment example. If we have which is size of 4, we would use address which is multiple of 4. So 4 is the, let's say address 4 is a good candidate to hold this object, but like address 6 or address 7 is not a good address to hold an integer. So if we in the structure we have to select the proper address to keep the objects. Um, that's the reason when we have some struct data structure, we may find the size of a struct is more than the size of each element. And that's because in between we have to choose the right starting address for a certain item. So we may see some empty spaces in between. That's the reason we have such a oversized um, struct. Today we will talk about one specific phenomenon in the C program, which is called the buffer overflow. So first of all, how many of you heard of this buffer overflow or buffer overflow attacks? Is this your first time to hear this buffer overflow attack?
I've heard of it.
Okay, great.
I've also heard.
Okay, great. Today we will um, we will talk about buffer overflow or buffer overflow attacks. This is quite a classic issue in C programming. Um, dates back 1990s. We have many flaws in the software bugs in the C program, and many of them is because of this buffer overflow um, issue. And this buffer overflow just make your program pretty vulnerable, especially if you put your program in a server and the millions of users around the world would access your C program and trying to do something in your server, then that would become a much serious issue. And now let's look at what is buffer overflow. This is quite a good analogy. We have basket. If we fill more water than its capacity, then the water will spill. And a pretty much a similar situation when we talk about buffer. Now, let's look at a demo I created, and let me show you what is the program typically look like for buffer overflow attacks and how we can do such attack. Okay, let me open my terminal. Okay. So I logged in to Blanca. So this is the Linux machine you can access as well. The way you can access, again, let me show you, is SSH your username, Blanca, uccs.edu, and then give the password, and then you can access it. No matter you have the Windows machine, Mac, or Linux, you can just find your terminal and use SSH, and then you can log into this Blanca machine. Before you log in, you have to use UCCS VPN. And I already created a program, and this program looks like this. Oh, sorry, buffer. This program, you can see, it's pretty straightforward. We have a main function, and in the main function, we make a function called echo. And this function echo, you can see in this function, what we do is we create a buffer which have 8 bytes, and the function gets would read from the standard input, or put it simply, just read your keyboard, and then get the 8 characters, put that in the buffer, and then we use puts. This function is trying to print out what we just inputted. So this echo is just read from the standard input and then print out what just being given. You can see here the buffer. There's 8 bytes, and some of you already recognize this is the buffer. This is just like the basket we're gonna overfill, and we should see some overflow issues. And here you can see I also created a function 1. This function 1 is just to have a printf. We just want to print out the message to know that we execute the function 1, and then this is the program I want to talk about. And this program is very problematic. In the following demo, I would show you why this program is problematic, how we overfill the buffer, and the outcome is quite surprising. We are able to manipulate this C program to run the func1. So from right now, from the C programming language, the main function only execute echo, right? This is the only function we're gonna execute. So in the following demo, you would find out we are able to manipulate this program, not only execute echo, but we're able to execute func1. Let me show you how to do that. So first of all, let me compile this program. And here, I would turn off the GCC's protection of the buffer. So we will talk about this later. No stack. So we just use this flag, no stack protector. We just turn off some security features so that we can show the buffer overflow in full scale. And we compile this this program, and you already see that GCC, because buffer overflow has been a quite classic issue in the past, so GCC already include the warning messages if some of the buffer flow potential has been detected. The warning you can see is gets is deprecated. This function just quite vulnerable to buffer overflow attack. And now let's just run this program. Let's just type something, 1, 2, 3, okay? And you can see here how this function would behave, how this C program behave. We give 1, 2, 3 as a standard input, and then the program just echo the input to be the output, 1, 2, 3. It's pretty much simple. Now, let's first use the GDB to look at what does function look like and what we can do about it. So we use GDB buffer. We get into GDB, and right now for the GDB we want to disassemble main function. You can see here is the main function. We make the function call to the echo. So it is what we perceived from the C program. Now let's display as echo. For the echo, we can see at the very beginning, we're trying to prepare a buffer, LEA. You probably recognize LEA. We get the address RBP -10. We get the address, give it to REX, and move REX to RDI. That is the RDI right now is having the buffer's address, and this is the first parameter, buffer's address, to the gets function. And we make the function call gets. So this would listen to the standard input and find any characters we just typed in, and then place the characters in the RDI pointer, which is a buffer. And then in the following, we give we get the buffer's address, and before we make a function called puts, this is to print out the buffer. Okay, this is pretty much echo. Now let's try this. How about when we read from standard input, we make a breakpoint. Let's check what has happened. So I will make a breakpoint right here, and I will run the program. And the program has been started. Let's type 1, 2, 3. Okay, this is just the input we selected. And you can see here, we make the breakpoint at a 1, 2, 3. And now let's say as echo. So you find the arrow is right here. So our program is about to execute LEA instruction. So now let's check something. Let's check about RBP. We want to print out the stacks and look at what does stack look like. One thing you can use is info frame. Info, you can use many things, registers. So you will print out the registers values. Right now, if you put down info frame, it will give you many relevant information about the stack. So you can see here, we are looking at, you can look at the information RIP instruction pointer, which is now 400586. So this is the instruction we're about to execute. In the saved RIP, you may probably recognize, if we look at main function, 4005C2. 4005C2. So it's a next instructions address after call. So that's a return address, right? Saved RIP is the return address. That is address we're supposed to return to after finish echo. And also you can read other informations. it gives you RBP right now is this number. This is a memory address pointed by the base pointer. Okay, so now we will do this. We want to print out what does the stack look like. And the way we can print out memory is X. We talked about this. X is try to print out memory. We want to print out in the binary form. So we want to, not a binary form. We want to print out in the hexadecimal form. And we hope each part is just a 1 byte. So we put down B. So we will check 1 byte by 1 byte. We need let's put down number 32. We want to look at 32 bytes from RBP. Okay, let's see what will happen. So it printed out the messages. You can see here, RBP is the number ended with A0. That is RBP. And for RB, let's just analyze this stack. Starting from A0, you can see we have something at the place, and here 1A8. This is other things. If we look at the echo, it seems like we have RBP minus 10. So you can see here, the RSP, the second line makes RSP equals to RBP. And then we subtract RSP with 10. And then we LEA, try to extract the address of the buffer, put that to RAX. So we know that the address of the buffer right now is RBP minus 10. So right now we don't have the RBP minus 10, right? So we need to try to improve our printout message. We want to also include the RBP minus 10 part as well. So we print out again. Okay, and you see here for the 90 part, we see 31, 32, 33 in hex. And that actually is the 3 characters we just give to the input. We type 1, 2, 3, and 1, this character in hex in the ASCII2 code, it is 3-1 in hex, and the 2 in hex in the ASCII2 code, that is 3-2. 3 in ASCII2 code is 3-3. So that is the 1, 2, 3 we just input. And we can find that we still have 5 places empty. We just fill with zeros. And now let's make a. So far, do you have any questions? Okay, let's continue. Now you can find the input right here. And the next part, we want to look at what is the other stuff. If we look at RBP itself, let's just put down 8 bytes. If you look at our RBP, the base pointer, it is B0, E1, FFF, 7F. Okay, let's look at where this number comes from. TCS echo. So you can see we have something as a base pointer. Okay, let's see. Here is the place we initialize the base pointer. And this base pointer unit should be having the old RBP. So the first one, we just push RBP on the stack. And then we move the stack pointer to be the base pointer. Maybe I will show you this way. Okay, let's find here. Okay, that looks better. So let's follow this this echo program. At the very beginning, we push RBP on the stack. Let's just use this one to be the RBP. We put on the stack. As long as we put on the stack, our pointer RFP is always points to the top of the stack, right? This is the setup. And this RBP belongs to the main function. We talked about RBP is callee saved register. So we need to push RBP on the stack, and this is to save RBP for the main function. So this RBP is the main function's base pointer. And the RSP right now points to the RBP. Now, next step, we move RSP to RBP. That means, change the color. That means right now, our echo functions be the RSP. Okay. They all point to the same space. Now let's look at next one. Next one, we subtract 10 from RSP. That, in our case, if we want to subtract, we just move the pointer downwards in terms of stack, that is expanding the stack. We move 10, that is 16 bytes. So actually, we will move the stack pointer over here. So base pointers be pointed here. And the next step, what we do is we LEA RBP minus 10 to REX. So we can make a guess. RBP is right here, minus 10 right here. This should be the buffer. This is the buffer. There is the RBP minus 10. Is there any questions when we follow through this program? Do you have any questions? Okay, let's fill out some of the stuff. We know that this 180 is a base pointer. And you can find the base pointer is pointing to B0, E1, FFFF, 7F. So we can know that the base pointer, right, the red base pointer, we can know its value. This base pointer RBP is B0, E1, FFF, seven F. Okay. This is the value for the base pointer. Because we just print out the message right here. This is the memory content for the base point for the memory content pointed by the base pointer, and here is the base pointer, right? So this is the slot pointed by the base pointer. So we know that the content in it should be this number. This is the main function's base pointer. Okay. Now let's look at other stuff. We see that from here, 90, this is RBP minus 10, right? This slot contains 31, 32, 33, right? That is, we put down 31, 31, 32, 33. Okay. And you may find that we finished this in buffer. We know that where this buffer is and what is put in the buffer. And also we know A0, this is a base pointer of the main function. And how about A8? What is A8? What is the C205400? What's that? What's that be? Did you make a guess? So we know the base pointer is the number ended with A0. We know this slot having the base pointer of the main function. And also we know 90, the number ended with 90. This is the place we have the 8 bytes buffer. And we also confirm that when we give 1, 2, 3, we can see the it's ASCII2 number 313233. And now my question is, how about the number ended with 88? What is that slot contains? I'll give you 1 minute. You can think about it. What is content in the A8 slot? Any idea? Okay, let me show you something. ECS main function. So you can check here. C20540. Do you have any idea now? So let me clarify. So you can see A8. You know, the content of the A8, this 8 bytes, is C2054000 and all zeros. And if you look at the main function, the address after the call instruction is something like this. We have 4005C2. Can you make guess? What is this?
It stores the addresses of those different memory locations.
Yeah, that's right. That is, if you look at A8, it is containing C2054000, right? If you look at the address after the function call, it is 4005C2. It is exactly the same thing, right? What do we call this 4005C2? It is the return address. This is the return address. This is the address when we finish echo function, we should return to it. Okay, maybe I need a slide to remind the part of the what I'm talking about. Let's look at here. Maybe I have clear access. Okay, this part we will go through again. Talk about how to make function, not control. Sorry, I have the wrong slides. Should be the slides. So in the part, let me show this one. So you can assume we have the main function, we have the echo function. When the main function trying to call the echo, so what we do is we put the return address, which is 400568. This is the address of the next instruction. This should be the address we're gonna return to. We put a return address on the stack. And then we update the stack pointer. And then we initialize the instruction pointer to be the callie's address. So next cycle, we would do the callie's address, right? So when we make function call, we push the return address on the stack. And in our example, the return address is the return address is, you can go to the main function after call instruction, and the return address would be 4005C2. This is the return address we should put on the stack. And when we check the stack, this return address is over here, right? So, any questions? Why this highlighted part is having the return address?
Why does it store all three of those memory locations versus just one at, like, say for example C2 and progressing further thereafter that?
So let me clarify, Nico. So your question is why we have three numbers and followed by many zeros?
Well, so why does it store the three addresses versus just storing one and returning to that same address, or that just one address?
Three addresses? By
Yeah.
three, you mean?
Then 05 and then 0x40.
Oh, I see your question. Okay, the together is one address, and this address is 4005C2. Combined together, this is one address. But because this address, it have 8 bytes, right? We need a 8 bytes to store this address, and we put the last 2 digits in 1 byte. This is C2. This is 1 byte, and the 05, the second byte, 40, the third byte, and the rest of the bytes are zeros. So altogether, these 8 bytes altogether, they are one single address.
I was looking at the address wrong. That makes sense now.
Okay, great. Yeah, great question. Thank you. Other questions? Okay. Let's remember this 88, the highlighted area, this is the return address. And 313233 right here is the characters we just input. Let me continue this process. Let's see, we run again. This time, we would put down 1, 2, 3, 4, 5, 6, 7, 8. We give 8 characters. We're supposed to occupy all the buffers, right? We still look at the same place. Let's see what happens. So right now, we give 8 characters, and from 90, this is the buffer. So we can see 31, 32, 33, 34, 35, 36, 37, 38, right? And we occupy 8 bytes of it. And if you look at A8, it is still having the same return address, right? C20540. So nothing changed over here. Let's just rerun the program again. This time, I give 1, 2, 3, 4, 5, 6, 7, 8. This is the 8 characters occupying all the buffer. How about I just give another 1, 2, 3, 4, 5, 6, 7, 8. This is not supposed to happen, right? But buffer is just 8 bytes, and I give 16 characters. This should overflow the buffer, right? Let's see what would happen. We still do the same thing. Let's check. So you can see here, 31, 32, 33, 34, 35, 36, 37, 38. That's no problem. That's the buffer 8 bytes. And you can see here, the extra 1, 2, 3, 4, 5, 6, 7, 8, it comes here. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 8. Okay. And we talk about A8. It still have the return address C1, C2, 0, 5, 4, 0, right? Do you sense what I'm doing? So you can see here, if we give more inputs, it seems kind of coming closer to the return address. Then a theory may flow that whether our inputs 1, 2, 3, 4, 5, 6, 7, 8, if give more, it could penetrate the barriers and enter the region of return address. How about we give more characters when we do the input? Is the input will keep going to overflow or overwrite the places we have the return address? That's a theory we want to test on. Now, let's just try it out. How about we run again? This time I give 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we give we should occupy the 9098 part. Now we want to overflow A0. So we want to 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's run the program and print out the message again. Well, you can see here, we overwrite the A0 part. We talk about A0 is having the base pointer of main function, but it seems like we change this memory content to be just the input we just type. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 8. Okay. How about we continue? Right? We can continue, right? This time we run again. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 7, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this right now we overflow. We overflow the first 3 lines. Now we want to overflow the return address as well. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's see whether we did it or not. Okay, we did it. We overflow the return address. Now it's having 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 8. Okay, it seems like we overflow the return address. Could you guess what would happen then? Segmentation fault, right? Why we have this segmentation fault? Let me show you the slides again. Now, let's see, we want to return. The echo want to return. Where are we going to return to? We find the return address on the stack. So 400568, this is the right return address. We just pop that to our IP. So the instruction pointer would be 400568. And then after the cycle, we would go to 400568 to execute the program. So the return address on the stack tells where to return to. No problem, right? Now, if our return address now is 3132, 33, 34, and this just guide our echo function to return to address 31, 32, 33, 34, 35, 36, 37, 38. Okay, that's the wrong address, right? That is not the correct return address. and it's not surprising our function just our program just crashed, right? So this is quite a demo about the buffer overflow issues. So far, do you have any questions? So in the following, you may find out this would be quite a delicate engineering. How about I just mentioned we actually can execute the function of func1. Sorry, this is func1. Func1. Okay. So we have the control. What the return address could be? We can give that in the input. Now we know that the address of func1 is 40057B. This is the return. This is the address for func1. How about we make the return address? We just show you the return address here. How about we make the return address here to be the address of func1? Then, after the function call, instead of returning to some random places, we actually can return to func1. And then we can execute func1, right? We can execute func1 if we place the func1's address at this place. Let's see whether we can do it. So remember, func1's return address is 40057D. Okay. So first of all, actually I have the answers. That is in command. Here's a way we can create an input like that. Okay, let me first show you. We need to write down it. Let me find the address of it. We want this to be the return address. Okay, let's write down here. We want to 40057D. 40057D. 057D. This is the address for func1. Okay, let's craft an address like that. So we need to give the input 1, 2, 3, 4, 5, 6, 7, and we have to input something like 40057D. The way we can make an input is use echo. So the echo could input something that is not printable, right? If we want to input a 3.1 in ask2 code 3.1, we just type 1. 3.2 type 2, 3.3 type 3. But how about 4.0 and 0.5.7D? So they are not standard ask2 code that you can type your keyboard to input. So we need some way to make it happen. The way to do it is use escape. You can put down the hex right here, 40057D. This is how we trying to craft an input which is 40057D. Okay. And in front, we need something like a 1, 2, 3, 4, 5, 6, 7, 8. This is occupy the buffer. 1, 2, 3, 4, 5, 6, 7, 8. That is occupy the next 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8. This is to occupy the base pointer, the main function space pointer. So 40057D, we need a, because it's a little endian, we should place the 7D first. We should place the 7D first, and the 40 after it. We also need a lot of zeros. We need another 3. Okay, this should be able to give us input. We just put that input as CC. Okay, if we look at CC, that is input we just created. In this input, the first 1, 2, 3, 4, 5, 6, 7, that is try to occupy the buffer. The next 1, 2, 3, 4, 5, 6, 7, 8, that is occupy some random space in between. And the next one is try to occupy the base pointer. And the 7D0540, that's trying to create the func1's return address. Let's just, now the created input is in CC. Let's just rerun the program, gdb buffer, this is echo. We still make the same breakpoint. Let's see what would happen. Run the program. If we want to fix, we want to feed that kind of input to the program, because some of them we cannot type directly. So we just give the files cc to R, to the running program. So in this example, we can still print out 32 bytes, and each one have 1 byte, and RBP minus Z. And let's look at it. So it seems like we did our job. So we overflow the first 3 columns, first 3 rows with 1, 2, 3, 4, 5, 6, 7, 8. And then the last part, this is supposed to be the return address. We make that to be 7D0540, and then let's check the func1. And you can see here, this is the func1's address. We are able to make the return address to be the address of func1, 7D054000, right? Let's just try to execute the program and see whether we can jump to func1. DCS echo. So we type next I. Next I, where we are now. Okay, we about to got the function. We can do the same thing again. Okay, this is main echo, sorry. Then we about to make leave the echo function. Next I, this is echo. So we about to return. Let's see where we return to. Next I. Okay, so you can see here, we actually end up in func1. This is func1. So you can see here, the arrow now is pointing to func1. We're about to execute func1. Let's just continue the program. So you see, we execute func1, which is not supposed to happen. Let's just exit the GDB debugging environment. Let me just show you. We run the buffer. This is the way feed the program with the input we just created. And this buffer have the main function only execute echo, but when you run it, you can see it. We actually being able to execute the func1 because we changed the return address to be the address of func1. So func1 is being touched. Okay, this is quite a demo for buffer overflow attacks. Do you have any questions so far? Did you follow my demo and understand what I'm doing, or you are confused? I feel free to raise it up, and I can explain more about buffer overflow attack. Okay, great. In case you have confusions, just raise it up right now so I can help you right away. Okay. So let me quickly summarize what we do. So if you look at the function buffer.c, the main function only execute echo. And the func1, we don't have a chance to execute it. It's not included in the main function. But when we do a buffer overflow attack, we just give more inputs than is supposed to give, and then just ECS echo make breakpoint run with CC x 32 bx RDP minus. Okay, so we give more inputs than 8 bytes. So the more inputs would overflow the buffer, and here it overflows the base pointer part. Finally, it overflows the return address. And we can craft our input to make the return address to be the address of func1. Then after echo wants to return, we actually returns to func1 instead of the main function. And at that place, we are able to execute function 1 instead. And that's the reason we are able to execute, see the func1's printout, execute func1. So that is to show us by using buffer overflow, we can execute functions at our will as long as we specify the return address to be the address of the target function we're gonna execute. This is the buffer overflow. And okay. If you don't have questions, let me create an exercise for you. Okay. So right now, if you have access to Blanca, you can access my program. I will copy that to the okay. So we will do a live buffer flow attack. I will share the buffer right now. It has been slightly changed. Now you are supposed to craft your own inputs to make this buffer flow attack to execute func1 as well. Now trying to think where I do this. This is share. Yes. Copy. Oh, I see. Now, let's do a pop exercise, pop quiz. So right now I have the buffer program right here, and you can find my program from Blanca using this path. Now I will give you 10 minutes. You can look at how to craft an input that can make this program execute func1. And you can submit your inputs to a folder. Let me see. Create folder CS2060. Do that. You can submit your inputs right here. Let me type it.
Can you show the file directory again? And are we able to just to copy that to our own directory, or do we have to work on it in yours?
You can use mine. You can use mine if you wanna, or you can copy to your place. Either way. Okay, for some of you who don't have the access to Blanca, I will show the assembly, and you can try to figure out what the input should be. And don't worry, our pop quiz is graded by attendance. As long as you send me something, you should get the full credit. But still, welcome to try and see the assembly. Pop quiz submission. Okay, I type in the chat window. There's a submission directory, and let me show you where's the pop. And the buffer program is located as a directory. I also send it out. These are two directories you can work out. Let me show right now. This buffer. So you are supposed to submit a file using your username, something that is recognizable to you, a file which is just like the CC I just showed you. Create a CC, which create your file, including the inputs, and then copy that file to my submission folder. And I will show you what does the buffer look like. It is slightly changed. So some addresses are no longer the same, supposed to be. Let's see, echo. There's the echo. And here is the func1. Well, sorry, it's the same. What I would do. Let me, bear me a moment, I just change it. Okay, I updated the buffer. Let me show you the new buffer. Yes, echo. Yes, func1. Okay. Okay, let's see. What's the question? A question from Matthew. Where do we submit our answer if we don't have access to Blanca at the moment? So you can email me your answer. Send me an email. And you can right now see the assembly from our session. It shows the echoes, and it shows the func1, and you should have the sufficient information to craft input. The only downside is you cannot try. But yeah, feel free to send me emails, including the answers. A question from Luke. I'm confused on what we're creating to submit. And in the demo, I created a file myself, CC. And this file, including the inputs I want to give to the buffer. And this file, you just create a similar file, but with the file name to be your username. And the inside of the file is the input you crafted. And then you just copy that file to my submission folder. Another question from Kelly and Wesley is you don't understand about the directions. So what I'm right now hope you to do is you can find the buffer program from the folder I gave it to you. You can find the program and then use GDB, go through the same process as I just showed the demo. You would be able to look at the assembly code of this buffer. And our goal is to have this buffer to execute func1 or to conduct the buffer overflow attack. You can feed the buffer with your special inputs. There should be some inputs you can craft that make this buffer to execute func1. And this inputs is what we need. You can create a file, including the inputs you crafted, and then upload the file to the submission folder or send to me by email. Okay, so do you have some questions? Is it clear or not?
Yeah, I have a question.
Yeah,
so when we find the memory address where the buffer flow is, do you want us to, like, what do you want us to overflow into the, or like, what do you want us to input into the overflow? Like, is it the memory address for the start of func1 or?
Yeah, you're right. The start of the func1.
Okay.
Yeah. Okay. Yeah, sure. A question from Dylan. Will we go through the answer after? I'm also still lost. Sure, I will do the buffer flow after you make the submissions in this class. Yes, we can do that. The basic idea for the buffer flow is you have a buffer, and in our demo we have 8 bytes, but as a user, it can type more than 8 characters, and in such case, you will find that the buffer would be overflowed, and the extra characters start to overwrite your stack. And because our return address is on the stack, at some point, the extra characters could overwrite the return address. In the demo, we show we can craft our input so that we overflow the return address, overwrite the return address purposely to be the address of func1. When echo try to return, it is not returned to main function, but returned to the func1. And start from there, we start to execute func1. That's a buffer flow attack. And not all the inputs could make the buffer flow attack success. We have to craft a specific one that return to func1 and see the printf message from func1. That's a special inputs we want to see, and you can put that inputs in your file, and then upload to my submission folder or send it to me by email. Let me try to double check with the buffer. Maybe there's that's weird. I gave all the rights right now. Should have to execute. That's just the top. Okay, great. It's working now. Let me show you buffer. This is echo. This is one. Okay, let me no symbol. Let's see. So first question from Luke. I'm getting the error no symbol table loaded. And my side, I don't have the problem. I don't know how I can solve this issue. Maybe let me type this as Apple. Luke, you try this and see whether you still have the error. Let me check the submission. Okay, great. Victor, I see your submission. Now we have 7 submissions. No problem. Question from Dent. So just to be clear, it's a file we made to submit, and the said file should have the input, correct? Yes. Yes, a file having the input. No problem. Or to make a buffer this program to execute function 1, how we can prepare input like that.
Just to clarify, so the address we want to overflow is going to be that 4005 FD, right? In func 1?
Yes, 4005 FD. That's
Okay,
right.
cool. And then you said, where did you say you wanted the file submitted?
In the chat window, copy that. I just copy the message right now in the chat window.
Okay.
Yeah. Let me try some of your submissions. Let's see whether it could work. A question from Dan. Also, is this like the previous pop quiz where we need to submit by the end of class? Yes, that's right. Submit by the end of the class. Right now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 14 submissions. We probably have about 30 students today. Yeah. I'll give you another 7 minutes. 5 minutes. Then I can go through how we can prepare input to overflow this buffer. A question from Joshua. How do you feed the text file input into buffer? So I typed the commands. You can do that. Yeah, thank you, Nicholas. That's the right one. So we have the redirection, use the smaller than sign. So we redirect the input file and give the content to the buffer format. Okay, let's do this buffer flow together. So first of all, we still want to make breakpoint at echo. We will put it here. And now, when we read the echo, you can see the buffer right now, the address is RBP minus 20. This is the address for the buffer. So it's no longer minus 10, but a minus 20. And also we introduce a local variable, which is RBP minus 4, which is have the value 10. We introduce a local variable, but it doesn't matter. So RBP minus 20, this is the place where our buffer is. Let's run the program. Let's type 1, 2, 3, 4, 5, 6, 7, 8. And then let's look at the stack. Let's do 32. And now RBP, we want to look at the buffer at first. So we type 0x20. It should give the address of our, should give the memory contents from our buffer. So you can see here, the first line is a buffer, right? We contain the typed characters 1, 2, 3, 4, 5, 6, 7, 8, and then the next one. This is RBP minus 20. The next line is RBP minus, let me see, RBP minus 20, and that is 32 bytes. So we need to do more. Maybe put down 64. Let's just have 64 of them. So the first line is RBP minus 20. Next one is RBP minus 18, RBP minus 10, RBP minus 8. This is RBP. Oh, we can print it out actually. Print RBP. Okay, RBP is A0. So here is RBP. And in front, A0889098. This is space we need to fill out. A0 is the base pointer, and we still the same reason. The base pointer right now is having the base pointer of the main function, E0, E1, FF, 7F. This is the main function's base pointer. And A8, this is the return address we're gonna overflow. So we need to start from 3.1, the place of 3.1, and then fill out all the spaces in between. Fill out all these spaces, and then finally reach the return address to write the return address to be the address of func1. And we can count how many characters we need to input. 3.1, this is 1, 2, 3, 4, 5, 6, 7, 8. Each line, that is 8 characters. 16 characters. 24, 24, 32. We need a 32 from here. And 40. We need 40 characters in order to overflow the highlighted area. 40 characters. And beyond the 40, we start to overflow the return address. So it should be 40 characters plus the return address, right? And let's see, what should be the return address? That is func1. Return address should be 4005FP. Let's try to create the input. We still use echo. Now we need 40 characters. Let's do it this way. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is 24. 1, 2, 3, 4, 5, 6, 7, 8. This is 32. 1, 2, 3, 4, 5, 6, 7, 8. This should be 40. These 40 characters would overflow the space, and now we need to specify the return address to be the func1. So we could put down 0xFD, 0x05, 0x40, and in front of it it's zeros. How many zeros? 1, 2, 3, 4, 5, 6, maybe more. 1, 2, 3, 4, 5, 6, 7, 8. Okay. We need to have 5 zeros. So this should be a good input to overflow it. And because we use the escape way, so we need to put down -e, and this should be creating a good input. We make that to be any file. Let's see, cc again. This is the name. This is the content of it. Let's try and see whether we can overflow it. cc. Okay, so execute func1. So we are able to execute func1 using cc. Let me remove cc. Okay. Is there any questions? How we overflow this buffer program and execute func1? So we just find where the buffer is, and then we figure out how many spaces we're gonna fill out with characters, and then we calculate that, figure out where the return address. So we are able to craft some random inputs to fill out the spaces and some specially crafted value to overflow the return address. Okay, yeah, Roman, I forgot how to do the file parts, but my idea is right. Yes. Let me show you how to do the file parts. It is echo because we want to input a value which is fd. We cannot type something that is fd 05 or something like that. So we need to escape that. So we can use the echo. This is command to echo this message. -e is escape. That is to make the /x to happen. /x, you can put down the hexadecimal number over there. So they would interpret that as input. This is how to create a input. You can see the input is some parts that is not printable. That means you cannot type directly into the terminal. So this is the way we can create something non-printable, but still able to feed it to a program. Okay. Any other questions? Oh, hi, Roman. In case you didn't submit to the submission folder, you need to submit to the submission folder. So I see your answers at the buffer folder. That is.
Oh, my bad. I left it in there. I sent it to the submission folder as well. I can get rid of that.
Okay. So I will delete it. Okay.
Yeah, I can get rid of it. Just give me a second.
Okay. Yeah, Victor, no problem. So sometimes take some time, figure out how many 1, 2, 3, 4, 5, 6, 8, try to build that. I use 1, 2, 3, 4, 5, 6, 8 just because it's easier to count. You can put down any characters you want. As long as the number of characters is the same, then it should work the same. Danny, wait, is there a submission folder? Yes, we have submission folder. Let me show you the submission folder. Yeah. Submission folder is over here. This is submission folder. Okay, let's see. We have many submissions right now. Okay. Yeah, let's take 10 minutes break, and we would come back and talk about more about buffer flow and how to protect from it. Okay, see you 3:35. Oh, sorry, I'm a bit late. Let me see this video. Oh yeah, it's pretty good. Uh, uh, let me read the comments. Yeah, Roman, that's a good comment. Good way to find out how many times we need 8 characters is to see how much we can subtract minus 20 and divide it by 8. And the RBP ahead of the return value. That's right. Yeah, that's a pretty good comment. As long as we can figure out the layout of the stack, so we can figure out how many characters we need in order to overflow properly. Okay. And do you have other questions? Okay, let's continue about buffer overflow. If we look at the program, the fundamental issue is for the C is it doesn't have the boundary check. We have the 8 characters, and we allow the user to give inputs to write into these buffers, but we didn't check the boundary of the buffer. Has the boundary of the buffer has been overflowed or not? So this is quite a fundamental issue in C. You have no ways to check boundaries of the buffer implicitly. So that's why when we try to use the C program, many times when we want to write into a buffer, we need to do a check manually that the numbers of bytes is proper for the buffer, not overflowing the buffer. That's what makes buffer overflow happen because of the lack of boundary check in C. And this buffer overflow was quite popular 30 years ago, and many attacks on the softwares coming from this buffer overflow attack. And even today, people still write a C program which have buffer overflow issues. And the next question is how we can prevent this buffer overflow attacks as a programmer. So very first thing, do a boundary check when you take inputs from standard input. One thing you can check some C programs, C functions. The later ones, they include how many characters they are able to receive it. If beyond that number, we would raise the question, we raise the error. So the later functions of C carries this boundary check functionality for you. So you can use these kind of functions. And for the gets, you see the error message. Gets is no longer safe. So please use other functions instead of gets. So when we can solve the buffer overflow is we can train your programmers to be able to write buffer overflow attack safe programs so that we can prevent it. But yeah, that's training the programmers. And this is a straightforward way, but also the less reliable way. So we are humans, we make mistakes. We continue to see programmers make mistakes occasionally, and this could be used by the attackers. That's why right now we still see buffer overflow issues in the C program. So we need to think about other ways to prevent buffer overflow. How we can do that? So one idea is to randomize the stack. In our cases, we know that the return first comes return address, then the main function's RBP, then the buffers which we try to attack. And the idea of randomization is to make attacker very difficult to find the return address. And for example, when we start the stack, start the program, we are able to find the func1's address. We know this is the address we want to jump to, and then we craft the input for it using this func1's address. How about we randomize our memory so that every time we run this program, the address of func1 would be changed every time. And if this address is changed every time, it's very hard for the attacker to craft some meaningful inputs to make the program jump to func1. That will be very hard. Yes, the attacker can still overwrite the return address, no problem. It can still do that, overwrite the return address. But it doesn't know what would be the return addresses reliably. It doesn't know reliably what will be the return address of func1. So it will make the buffer overflow attack happen. It still can happen, but its impact is dramatically reduced because the attacker cannot execute random functions from here. Then that buffer overflow attack doesn't make a big impact. This is one idea. We can randomize our memory every time when we run the program buffer. We just insert some random sizes of memory in front of the program so that the address of the func1 would be randomized. This is a way, one way to prevent buffer overflow attack. The second way, which I like better, is called a canary. So canary, you may know the real world example of canary example. So there is a cave. You don't know whether the cave have enough oxygen, and you really want to go into it. And how about how we can test whether the cave just have the oxygen? You can have the bird and fly that bird into the cave. If the bird is still alive, flying back, it should be fine. If not, that means oxygen is not in the cave, and you probably have to avoid that cave. So it's the same kind of idea. We wanna in the previous technique, we try to prevent the buffer overflow attack to execute func1 in our example. Here, we want to have this canary mechanism in trying to detect buffer overflow if it happens. If we can detect, then we can just stop the program, right? We can stop the program right now and try to limit the damage, or we can report to write a program report to the administrator, and then administrator could take a closer look at what is going on. So this canary mechanism is trying to detect buffer overflow attack. And what we can do, and let's assume here is a buffer we wanna use. And here is the return address we want to protect. And you can see here, usually we have spaces in between, we need to fill it out. But for the canary cases, we actually fill out some random values. This is random value we want to fill out. And this random value would be checked whether it has been changed. Suppose there's two cases of scenario. Case one, we have the buffer overflow attack. If we have the buffer overflow attack, when we craft the input, the attacker doesn't know this random value. And what would happen? It would overwrite this canary part, this memory. It could be a variable. You can think about it as a variable, 4 bytes or 8 bytes. It will overflow this canary part with its input. And because the attacker doesn't know what should be the original random value, it would change the value of canary in very large probability. And when the program takes in the input, it can check whether this random value stays the original. If this random value, the canary value, has been changed, that is an indication that a buffer overflow attack has happened, right? If we have buffer overflow attack, the canary value would be changed, and then we detect buffer overflow attack. The other case is we don't have buffer overflow attack, no attack. What would happen? The original value stays the same. We check the original value and then find nothing, find no change, and then we can mostly safe to say there's no buffer overflow attack. So this is the way we can detect the buffer overflow attack. Any questions so far? Okay, let's still use our demo and look at how Canary could be used. Let's look at our terminal. Okay, right now, let me go to okay, what is a text string? Okay, there's a text string. And then we feed the buffer with cc. Okay. So we actually func one. Now, let's recompile the buffer without the, so previously we used a flag no stack protector, right? This is the original way we compile it. We want to show the buffer overflow attack can happen. Now we just don't take this part. It will install the canary for our buffer. So let's look at buffer again. We know the echo function is vulnerable. Let's just look at echo again. And well, it didn't install it. Let me manually turn it on. protector. This. Okay, here we go. So the Blanca defaultly don't turn on the protector. Is that the case? Well, that would be an issue. Well, that's the issue. Okay, usually the Linux system right now, they would turn on the stack protector automatically. But for Blanca, GCC, the program GCC, defaultly turn off the stack protector. So be careful when you use the Blanca. So the GCC by default is not safe. Let's turn on the protector manually. That is to use this flag -f stack protector. It will turn on the protection. And let's look at the GDB. Look at the echo message again. GDB, what's that? Buffer, this AS echo. So right here, you can see something happen. When we still have the RBP -20 to be the buffer's address, but you can see here we move a number. FS is the segmentation number. So this is an older way of doing addressing in assembly. Right now we don't use it quite often, but this is quite an older fashioned way to do it. It's basically FS is a section. In this section, we offset by 2.8. So this is a place holding that canary, the space which have the canary value. Remove the canary value, FS with 2.8. We move this canary value to RAX. And then move RAX to RBP -8. So we can actually check the canary value right here. Let's take a breakpoint right here. Run it, 1, 2, 3, X. This AS echo. Now let's look at 48 BX RBP minus 20. Okay, so here we see the RBP -20. Let's see RBP. RBP is still A0. Where's A0? Oh, sorry. It's not 20. It's 0, 20. 0x20. And printed RBP A0. So A0 is right here. And also, if you see the echo message, we move the canary value to RBP -8. RBP is A0 -8 would be 9.8. So here is the canary value. And here's the canary value we installed. The canary value is 00 EB 00 AD EB 272493. Okay, this is the canary value we just installed. And you can see here, between, this is a buffer we can overflow, right? The highlighted part is the buffer, we can overflow. And A8 still is the return address, but in between, we have the canary values. So you can imagine if we do the same trick, we would overflow the canary values first before we overflow the return address. If we overflow the canary value, the chances we don't know, the attacker don't know this value, and would change this value to be another one. By detecting whether this value has been changed, we can decide whether there's a buffer overflow attack. So how we make the check? If you look at the program in the following, so fs28, this is the place to hold the canary value. We need to store it before we make comparison. So here is we're trying to move the RBP -8, which is the canary value, to RAX. And this canary value is compared with the original FS28. If the two values are different, then we would not make the jump. We would call a function called stack chunk fail. This is just to report a stack overflow has been detected. We just make this function call to detect the fail. So you can see how it works. After the gets, we would compare the existing canary value with the original value. If the two values are different, we would stay and make the function call that is stack chunk fail. That's the way we detect the buffer overflow. And let me show you what would happen. Let me show you what would happen if we right now this buffer is installed by the canary value. If we right now feed the original attacking string to the buffer and see what would happen. Ooh, it's quite different, right? So you can read the message. Same stuff when we give the input to the buffer. Right now, the printout message is stack smashing detected. That means stack overflow detected. And the program is terminated. And also, it gives you all the debugging information, what has happened. And from the message, you see we didn't execute the func1 because the buffer flow has been detected. And the way to detect buffer flow is to check the canary value, whether the value is still the same. This is a buffer overflow detection. So let me retry that. If we okay, so if we don't have the protector, then we are able to execute func1. If we turn on the protector, we do the same thing, and we can detect the buffer overflow attack. Okay, so this is the canary. Is there any questions? Okay, Let's go back to our slides. This is the program I just showed you. We have the canary values, and we want to. The first box is to move the canary value to the stack, and the second box is trying to compare the canary value on the stack with our stored ones to see whether they are same. Okay, that's really last slides. Okay, so that is the buffer overflow attack. Feel free to try the program. I will leave the buffer program at the folder. After class, if you are interested in it, you can take the analysis and watch our videos, walk through every step, and you can conduct your own buffer overflow attacks. And I will just make the program over there for a while. And the idea is to summarize, the idea is just because we have that buffer, and we allow users to give input to fill that buffer. If some users give more inputs than it should be, then this buffer would be overflowed, and finally we would overflow the return address and make the attacker to be able to execute any random functions in your program. So this is buffer overflow attack, and actually that is the last chapter last section we want to talk about for the assembly language. And now let's make a summary about what we talked about in assembly. So you already noticed we use more than 1 month talk about the assembly language, and the common pattern is we have something in C. C have the variable, C have the function call, C have the if-else branching, looping, and the C has the function call, C has arithmetic operations. And you can see here, all the stuff was also supported in assembly. Assembly has a way to start the local variables. Assembly has the way to make function calls. Assembly has the way to make branching, looping. The assembly way to deal with array, struct, union, and you can see this is the 1-by-1 mapping, and that's pretty much why the C can have such functionality, because the assembly part could support this. We talk about this idea when we have the C program, it's higher level program, and if we want to run this program, the very first step is have a translator, which we call the compiler, to translate this C program into assembly. And by this translation, you can imagine everything that can happen in C should be able to happen in assembly as well. And for this assembly, we would have the second lab. The second lab is about the bound lab. For the bound lab, it's a piece of program. We'll have many sub-functions, and you are supposed to type some certain inputs, just like the homework to Func4. Func4 asks you for input, which make it return 1. And for the bound lab, we have the similar patterns of usage. you are reading the assembly code, and then you figure out what should be a good input. It organized as a BOM. If you give the right input, you pass that phase, and you get a scores. And if your input failed, then that phase would explode. You would get some points deducted. And we will have we actually will have a scoreboard to record how everyone is doing. But don't be afraid. That is acronym show on the scoreboard, not your username. Just the BOM and ID is not traceable. So you will know this is your BOM, but I will know for sure. But other people won't know that this is your BOM. And you can apply more than one BOMs. You can try it out. And for this, we will heavily use GDB to look into the BOM program and try to diffuse it. So that will be our BOM lab. For the assembly, another part is we need the way to learn this part is to practice. So assembly is a language, just like C program. The best way to learn this language is just through practice. You don't have to write your own assembly. You can read it. That's good enough. And we will have the BOM lab published soon. And I will have another lecture. Spend some time walking through some of the BOMs and what that means. Okay, that will be the BOM lab. Seems like this is today's contents. Do you have any questions so far?
Is there a limited number of attempts on the BOM lab, or can we try it as many times as we want?
Yeah, that's a good question. So practically, you can try as many times you want. We allow you to apply for new BOM. There's no limit how many BOMs you can apply. So you can try a lot of times, as long as you have one BOM, you think that you have the highest grade, that BOM will automatically be counted as the one. So you can try many times. Yeah. Any other questions?
We'll still be able to work with partners, correct? For the second lab? Okay.
That's right. You can have we can have a team of 2 people, so you can still work with another classmate.
When are you going to release this assignment or the lab?
I will have my TA to do that as soon as possible, probably next week.
Okay.
Yeah. That will be that one actually my favorite labs. Yeah. Okay. Any other questions? Okay. If you have questions, you can. Oh, there's a question. There's a question from Alex. Will we be doing all the homeworks that were originally scheduled? Yes, I will try to make that on schedule. So November, yeah, we still have time. Yeah, we can do that. So our the workload for the homework is far less than the workload lab. So the BOM lab, I think BOM lab would take the most time, and as our second lab, and then somehow we will have our third lab. there will also be a bonus lab as well. Yeah. Okay. If you don't have questions, I think that's all. That's all the contents today. And thank you for attending today's class. Remember, email me or submit the pop quiz input to me. A question from Dylan: will the lab be with partners again? Yes, you will have. You will able to have one partner, group size of 2. Okay, and I will be around if you have other questions. And thank you for attending, and have a great weekend.